happy to be here in the beautiful Novi Sad, as you can see. It's going to be a very sort of practically directed session that I hope will, if you're not already familiar with all the material, would help you to do practical science with climate and meteorological data. Let's just jump into that, shall we? So I will be jumping a bit between the presentation that I have and doing different demos. So I'm just going to share my whole screen, and we'll be jumping from the presentation and to various different demo things. So now you see the presentation. So, okay, let's see what happened here. So, again, technical issues. Okay, yeah. There we go. So. Here we go. Okay. So now you see my slide and just the one slide, right?
No, we don't see anything.
You don't see
screen.
Okay, now we do.
Now you do. Okay.
Yeah.
And now you see one slide and just the one slide.
Yep.
Yeah. Great. Then we're all happy. Okay, so let's just flip through the agenda. I'll talk briefly about what Net Cdf files are and why we would want them. We will do inspecting of Net Cdf files with NCDump, viewing Net Cdf files with NCView, obtaining climate model data from EXtremeClimTwin, obtaining reanalysis data, and then we will focus on the Copernicus data store. We will do some manipulation of Net Cdf files using Cdo, some manipulation of Net Cdf files using NCO, and some working with Net Cdf data in Python, just briefly in the end. So what are Net Cdf files? So from Carly's talk, you remember maybe this illustration, and also remember that climate data are organized in grid boxes. So we divide the Earth up in different geographical grid little squares, and we model the climate in different vertical height levels, both above, and we can also model down into the ocean, down into the soil, and we get an awful lot of these little grid boxes where we have data, and in each grid point we have many different variables such as temperature, wind speed, humidity, and so on. And we have them for huge amounts of time points. So the climate model models the data time step by time step and write out data for all the time for some various time steps. So we got a really huge data set of high dimensions. So we need a format to keep these files. And what are the requirements of such a format? Well, climate models are not something that just one group of researchers do at their own institute. So various different climate models are being run all over the world by different research groups. And we also want to share the research data from various climate models between researchers in different countries and different groups. So that we can all understand the data and compare them, and we can compare the various climate model outputs. So we need a format that's internationally recognized and multidisciplinary recognized, so that it can be used both by climate scientists, but also by geoscientists, meteorologists, maybe even social scientists who want to use and economists who want to use the climate output data to do further modeling on impacts. As we saw from previously, it needs to be multidimensional. We have many different dimensions. We see that it's useful to have it be gridded, and this can also be the case if we want to save, say, observational data. So here the grid doesn't have to be this really regular grid, but it could rather be a grid where one of the dimensions is just a different observation stations that we have, maybe. For this reason, because it can be both observation data, gridded data, it could be large data sets, small data sets, it could be many dimensionals, it can have a vertical dimension, it might not have a vertical dimension. One file can contain data for many variables or just one variable. It needs to be quite flexible. And we need to also be able to append more data at the end. And it needs to be able to accommodate really large data. So, of course, NetCdf files can also be used for really small data sets, but the real challenge is the really large data sets that we typically encounter in climate modeling. So the answer to this is NetCdf files, which is a format that has been developed since the 80s in the US by the University Corporation of Atmospheric Research, UCAR, which is a US nonprofit umbrella organization for atmospheric science institutes. How does NetCdf answer this question? Well, in order to make it internationally recognizable and recognizable by various disciplines, it of course has a very strict formatting scheme, which the files conform to. But this format also includes metadata in the actual files. So information on units, information on what the missing values are. It can be information on who made the data, who you can contact in order to ask questions on maybe the data looks erroneous for some reason or stuff like that. Is actually included in the file itself. So it has metadata there. It is gridded, but it can, so it's organized by the dimensions of the file. So this can typically be time, longitude, latitude, vertical levels, and so on. But you can define the dimensions yourself. So the grid can be regular or irregular, and it can be based on stations, for instance, and so on. And this way you can hold many different types of data. And one of the dimensions can be unlimited, meaning that you can, for instance, grow the data over time along this dimension. This is typically the time dimension, which is for that. And finally, it's binary, which means that we can pack and hold the data as efficiently as possible, which is really, really useful for these really large data sets. And there are a few different versions that have come up since this has been developed since the 80s. It's to be expected that some things have changed over time, but almost all of them are sort of compatible with various types of NetCDF software. And some of the software that we will look at can even swap the data from one version to another. So for instance, NetCDF full format is often a bit more efficiently packed. That's the current version than previous versions. So sometimes you might be able to save some space by reformatting the data in that way. And the file extension is .nc or .nc4. So that's the type of file name that you'll be looking for CDF files. So as I said, the NetCDF files are binary, and that's kind of hard to look at and understand anything from for humans, whereas it's really easy for computers. So therefore, we need some kind of software to inspect and look at the contents to see what we have. So NCDump is one such type of software which converts the contents of the NetCDF files to ASCII format, which we can then dump to a file or read with some kind of editor like less to see some of it. And NetCDF also has a lot of options that you could add. So a normal NCDump command would be what you see here, but not the -h, and file.nc is just a file that we see. If we add the -h, we just get the header, so we just see the metadata, which can be quite useful oftentimes. -k will not actually give a huge ASCII output, but just tell us what NetCDF format we are looking at. So file type, NCDump-v, and then you can have a variable name, or you can have a list of variable names separated by comma. Will give you only the data for that particular variable. And here's a link to a man page for NCDump. So NCDump, here's some NCDump output, and I will show you now how we got to something like that in my screen. So now you see my screen, right? So here we have terminal window. So what we're going to do is look at the file called PR date Canny75. We'll look at this one. We'll put the output to less, because otherwise we'll just have all the output in a huge dump and we won't see anything useful. It's just going to be numbers flashing across the screen.
Marit, could you please make it a little bit bigger so that
even bigger?
Yes, a little bit.
Because I think it's just as big.
No, not the letters, but the whole whole window. I think.
Yeah,
yeah,
like so.
Better. Yes, thank you.
Yeah, we can even do this. Okay, so it starts by saying the file name, and then it lists the dimensions of the file, which are time and latitudes and longitudes, and also there's something called bounds. So for each of the dimensions, there is both the midpoint of that grid cell, but there is also some bounds that tell you the edges of that grid box or time frame also. So, and then we get the variable listed. So actually for each of the dimensions, there is also a corresponding variable, which says what the variable is at that time point. And similarly for the time bounds, there's both there are two of them, one for each bound for each time point. Same for latitudes and longitudes, and we see they have units. We can see that the calendar for the time unit is a 365-day calendar, so there are no leap days in this data set. That's not a normal thing to have for climate model data. So it's important to look at a lot of interesting information. It also says that the time variable is printed in the units of days since the 1st of January, 1850. So the days would be quite large numbers. And then finally, we have the variable that's actually contained in here, that's precipitation flux, and we see the units for that, different names, some comments, and so on how it came about, what the missing values are, and so on. And then come some global attributes, which are for the whole file. So there we have some, a lot of like dates on when the file was created, what kind of run it was that was run. We have an URL for more information. We see that it's a Canadian Centre for Climate Modelling and Analysis who did this simulation. We have a lot of information there. We have a contact address that you can send if you find out if there's something wrong with the file. You can send an email there and so on. So a lot of interesting info. And then after we've scrolled through that metadata, the data come. So and it starts with the first of the variables listed. So since time was listed first, we first get time variables, and we see that they have different, so 0.5 means that it's in the middle of that day. So the times are sort of defined to be the midpoint of each of the days. So if we add on -H, we will only see like the upper part with the metadata. If we do -V and we look at, for instance, longitudes, we can just see the longitude data, and we see which longitudes the midpoint of the grids are at. We can check the version, so here it says that it's, no, that wasn't correct. So yeah, that's because I kept the long in there in the command, sorry. So that's why I got an error message. So now you've seen an error message as well. So if we do -K, we see that it's a Net CDF for classic model. Okay. So now we looked at the file, we have more of a feeling of the data that's in the file from doing this. So let's return to the presentation. Another thing that we can do that's really useful to look at NetCDF data is look at it graphically. So for the most part, NetCDF data is geographical data, so it's nice to see it on the map. And you can use Panoply for this if you're more familiar. I like to use NCView, which is a viewer for NetCDF files. So let's look at this file with NCView. So here we see we get we can choose some different variables that we want to plot. If we plot the time bands and the lap bands, we will just get sort of a linear graph. It's not very interesting. So here is the precipitation data, and we see it's for 1 day. We have some options, so we can choose to have the coastlines be maybe a little bit smaller. We we can change which color scheme we want to show our data. So for instance, if we'd like, now it's whichever one is on the top is the one that's being used. So if I don't want this one, but maybe rather want this rainbow colored one, I can just put that one on top and enable that. So then we get a different scale. And usually there's a color bar here. For some reason, it didn't come in automatically here. So I did work last time I demoed it when I changed the color scale. But anyway, oftentimes, most of the time, you will get a range of what the colors mean here, but we didn't get that just now. And then we can move. So this is for 1 day for the first time point. It says the 2nd of January, but it's actually for the 1st of January because this is the end point of the grid box. So we can look at the next time step or the previous time step. And the previous is in this one will be the very last point in the time series of the end of the century. We can click ourselves through the time steps, but we can also have them move through so we can see how it changes overall. Okay. So let's return to the presentation. So where are we going to get all of this data? NetCdf files that we are looking for. I guess the last week, Carly showed you a little bit about EXtremeClimTwin, which is where we get most really big climate model data sets. So there are a lot of climate model data sets and people run their climate models for all sorts of things all of the time. But there are also these really big intercomparison projects where we compare how different climate models do compare to each other. And EXtremeClimTwin holds the data for these. So, for instance, CMIP6 is the newest really big intercomparison project. The last one for the last IPCC report was CMIP5. And there are also older CMIPs. In addition, there's intercomparison projects between regional models, which downscale and look at more regions. And the largest one of those is Cordex. And both Cordex and CMIP data are hosted on the EXtremeClimTwin. So the way that EXtremeClimTwin works is also contingent on, it's kind of the same thing for a sort of data repository as NetCdf. File format is for formatting. It sort of answers the question that we are supposed to be working and collaborating internationally, sharing data across really huge numbers of people and large data sets. So how do we best do that? Well, in principle, the way it's been worked out in EXtremeClimTwin is that there are several different or many different nodes or servers where you can go, log in and browse the data and find out what data you want and download them from there. But the data themselves are being hosted on also many different nodes. So for instance, the Canadian data that we just looked at are being hosted on a server in Canada. The Nordic climate model is being hosted on servers partially at least on the Norwegian national infrastructure model and so on. So models are where they are being run the data are in practice hosted, and then you can use this shared portal, which in a uniform way allows you to get the data from these various places. So here are a couple of examples of nodes that you can go to. This is the a US node and a German node. And we can look into those to try and get the data. And what also happens with all of these huge servers is that not all servers are up all the time. So here is a page where you can check the status of the various nodes at present. So sometimes you can't find data that you were expecting to see at one node. And sometimes that can be because that particular node from which you're browsing is somehow down, or it could be because the node on which the data hosted is down. And sometimes if it's the data that you're browsing from that has a problem, you might be able to find the data on a different node. So it's good to know a couple, 2, 3, 4 different nodes in which to get the data from, so that you can check another one if you can't find the data where you're looking. But sometimes if the server where the data are actually hosted are down, you just have to wait for that server to come back up in order to be able to turn on the data. But it's good to check the status. And not all nodes give you access to everything. So for instance, this German server gives you access to the codex data, whereas this US server doesn't. Yeah, so not all of them have all the data all the time. And there is also this really nice page with an errata. So when people do climate modeling, sometimes things go wrong for various reasons. And some things have to be rerun, or maybe the data won't be corrected at all, or maybe you have to do something yourself to correct the data. And on the errata page, you can get information on what the errors might be. And this also means that sometimes the data gets updated. So all of the data files on EXtremeClimTwin has a version number. And when you use the data in your research, it's really good to document somewhere which versions you were using, because in case the data being updated at a later stage, it's more easily reproducible what you did if you know which version you used. Okay, so let's jump in and look a bit at what it looks like going into EXtremeClimTwin. So let's just get my browser in here. So from the main page, if you click on CMIP 6, you will get this page, which is the search page. And let's see, for this page, we can then choose what we are looking for. So there are a huge host of options that we can choose from when we narrow down our search, because there are so incredibly many files. So let's say we're now looking for the data from the model CanESM. So the source ID is the model name, and we can see that there are really, really many models to choose from. But let's choose this CanESM model. The number in parentheses is the number of hits or categories of files that you find that this model has submitted. So CanESM 5 has 761,030 of these. So when we click search here, it updates everything also for the other categories. So if we want to go and look at the SSP, the historical experiment, so we looked at SSP 58 previously, so maybe we want to look at the historical experiment. Then we can look in the experiment, and now it's only showing the experiments which CanESM 5 ran. So there might be some additional experiments that they didn't run that other models have run that you can see if you haven't checked the CAN-E75 box. And let's say we want to find the precipitation data. So for this, we have to choose the correct variable, and the variable names in EXtremeClimTwin or in CMIP6 are particularly defined so that they're the same for all the models, but they're not all completely transparent what they mean. So there's a list of definitions, the link to which fell out of my presentation at some point, so I'll share that in the chat later. But precipitation variable is called PR. And let's say we want this on daily resolution. So frequency is what time resolution you have. There's 3 hourly, 6 hourly, daily. Fixed data, that would be orography or land sea masks or something like that. And let's check the daily and see what we get now. And when we search here, we see that there are 50 different sets of files for that. And the reason for this is, as Manfred asked for in a previous talk, that climate models would do well to not just do higher resolution, but also do more ensemble members so that we could check variability. Well, some models have been doing that, and CAN-E75 is one of them. So it has run 50 different ensembles for the same experiment so that people can look at the variability. And then we see that the hits that we have, they fill up these pages, which give you 10 and 10 results at a time. So there are 5 pages for the 50 total. And you can maybe see that I've already done this presentation once previously today and added all the first the ensemble members from the first page to my data card. So I forgot to say, but it's really useful to have an EXtremeClimTwin account. So if you haven't got one already, then get one, because when you have an account, both can you apply for access to data sets that aren't publicly available to everyone, like Codex, but you can also have a data card in which to put your data, and you can do much more useful things with downloading several data sets. So if you haven't got an account, what you can do is get this search result just the same way. And you can say, well, maybe I'm interested in this file. I can list the file, and I can click the HTTP download to download that file directly, which is perfectly possible. But of course, if you want these 10 files, or maybe even all of these 50 files, it's not much fun to be clicking all of these HTTP download things. So then we can just simply go through. So if we want the next 10 hits as well, we can go here and we can add all of these next 11 hits to our data card. And we can go to the data card. And here we can see that we have a lot of files added there. And we can select one or more of them, or all of them. And what we can then do is make a Wget script, which is a little script that you can run on your machine in order to download several files from EXtremeClimTwin at once. So I'm just going to do that. So there we have a Wget script. Also, if you're looking at CMIP5 rather than CMIP6 data, in that case, these data sets will include data not only for one variable, but for many variables at a time. And oftentimes you're not interested in more than one or a few of those variables. And what you then do is you can type the variable name here in the search field, apply that to all of the selected datasets, and then it will only show the datasets that include that variable. And when you click the wget script, that wget script will only be a wget script for that variable. So that's also very useful. Okay. So now we have a wget script to get our files. And what we do then is to run the wget script. So we use bash, because bash is the language in which the wget script is written. And we add a -h because that's necessary in order for us to send our username and password through. So we run that and we add our username or OpenID, as it's called. Which is really lengthy. And then you type your password and then it starts downloading. And the script is quite a sophisticated script, which both downloads and checks if it's been downloaded correctly by comparing something called a SHA. And with this, it can also, if you run some of these download scripts, over time, you'll find that not all of the downloads always work. And sometimes when you run it, it manages to download maybe half of the files and maybe not the other half. And in that case, you can just run the script again. And if the file's been downloaded before, it just checks that it's the correct file and then moves on to the next one. So it doesn't try to re-download all the files it downloaded before, which is really useful. Okay, so let's keep going. So obtaining reanalysis data. Reanalysis data sets are also really useful to get a hold of. So on this slide, I've just listed most of the URLs for why you can get the reanalysis data sets that Carly talked about. Here it's not as streamlined as for the climate data. So it's not one and the same page you can go to, and not one and the same download methodology, which is the same for all of them. But most of them have sort of fairly intuitive, or at least this good description of how you go about getting the data. They can be similar systems to what we saw for EXtremeClimTwin, where you toggle the various things that you have, or they might be where you sort of zoom in on the tree of the available files. And most of them will then either give you an FTP link where you can download the files for a limited time, or there could be some URLs that you get from which you can download the files using, for instance, the tricks that Tom taught you about downloading from URL addresses. And also for most of them, you might need to get an account somewhere in order to get access to the data. But that's also, it's just something that you need to do. And normally if you have a university affiliated email addresses, you will get one without any issue. So we will look more particularly at downloading reanalysis data from the Copernicus data store, because the download method there is a bit different, where it uses some Python scripts. It generates a little Python script that you can use to download with a particular software. And downloads from the EXtremeClimTwin site works in very much the same way, with a slightly different download methodology. well, it's slightly different software, and the download methodology is basically exactly the same. So let's have a look at that page. So first, we can look at the how to use the CDS API. So before we get started, we also need to register and make an account. And after that, we can use this guide, depending on what system we are on, for how to install the software to download from CDS. And after we downloaded the software, we also have to use a key that we get in our login account. And so to go to the download, this is the front page where we find the datasets. And there are many different datasets in here, not just reanalysis data. So for instance, there are climate indices and climate projections, satellite observations, seasonal forecasts, and observations. So lots of interesting data here. For instance, earlier today, you heard Jana talk about climate indices and ETT-CPI indices. And in 2 months or so, there will be a new data set on CDS that Carly and Jan and I and our collaborators have made on CDS, containing some of these climate indices calculated for all the CMIP6 models. So if we're looking at reanalysis, we then pick out the reanalysis and see here we can choose some different variable domains and spatial coverage. So here's also, if you choose Europe, you get the EURA reanalysis dataset, whereas global, you will get various versions of ERA5. So we are interested in total, say we are interested in total in precipitation on a daily basis from ERA5 to compare to the CANISM 5 set that we just looked at. And then we may look through the list and we might discover that ERA5 data are not on daily are not on daily resolution, but rather on hourly or monthly. So if we want daily data, we need to download hourly data and then transform it in order to get daily data. So for precipitation, we want ERA5 hourly data, and we want them on single levels. Because single levels is what you have for most of the surface variables. Then you have pressure levels for atmospheric values. So we go to that data set, and first we have an overview which tells us about how this reanalysis data set came about, lots of interesting metadata that can be very useful about licensing and so on. And to download, we go to download data. And then we can choose the variable. So precipitation is in the popular section, but there are lots of other variables that we can look for if we're interested in runoff, for instance, or evaporation. So it's fairly self-explanatory. Let's say we're interested in looking at the data for 2020 to compare to our precipitation projection from CANISM 5. We want to look at the whole year, all of the days, all of the time points. And then we can choose what region we want to look at. And this ERA5 has really high resolution. So even if it's just 1 year, and since it's hourly data, it's going to be quite a large data set. But let's say we're mostly interested not in the whole region, which is global, but rather in Southeast Europe. So then we can choose a subregion to extract. And I don't know, maybe you feel very offended by my choice of what is Southeast Europe, but I chose what I would consider to be a region encompassing at least all of Southeast Europe. So from west 30 to east 30, and from north 35 to 50 is the subregion that I've chosen. And then we choose Net Cdf files. Group files is also a quite common climate data format. There are ways of converting from GRIB to Net Cdf files. In general, Net Cdf files are a bit easier to work with and prefer them. At least I do. Then what we do is we show the API request. So then we get a little code snippet here. If we're logged in, we can actually run the code directly and get the file directly. I'm not logged in just now, so I can't do that. But then we can just copy all of this code and copy that into a file. So here it's been downloading a file. Let's just stop it from doing that. So I'm making, let's see, I need to do that first. So I'm opening a new file and I'm adding the code that I copied over there, and it copied it over some other stuff as well. So let's just take that out. Let's see where they go. So here's our code, and we can now just run the code as it is, or we can also change things if we want. So for instance, we can make a more useful name here. So we can say we can call it something like that. I also find these scripts really useful because we can also take them as part of a bigger script that does other things. So for instance, if we want to manipulate the files or the contents of the file a little bit, which we will look at later with Cdo and NCO, we can incorporate those commands into the same script and do it as a part of the download process directly. And then we can delete the original files, and we don't have to sit around with, for instance, hourly data if we transform to daily data, if that's what we want. So we don't have to sit around with such big files. Also for downloading from CDS, we can't download arbitrarily large files. So if we want the data not only for 2020, but for all of the years, say, we might not be able to get all of the data in one go. And then we could have a little loop, for instance, that loops over years, downloads the data for 1 year, maybe does some manipulations like turning the data into daily from hourly, and then moving on to the next one as well. That frees up more space where we download the files, and it also allows us to download all the data. And then we can have the script just running in the background, and we can come back after some time, and we have all the files that we really wanted. So that's really useful. So now I can just run that script. and it starts sending the request. And it downloaded the file really quickly. So it depends a bit on what the queue is like and so on. Oh, in the last demo, it was not this fast. Okay, so let's move on. Yeah. So then we go on to manipulating the files using Cdo first. Cdo is a software tool with a lot of different operators that we can use to do hundreds and hundreds of different things to see in NetCDF files. And since NetCDF files has this weird binary format and the dimensions are a bit sort of difficult to keep track of, it's really useful to use a tool like this because it keeps everything straight and it gives you in one line or just a few lines the opportunity to manipulate the files in somewhat more intuitive ways, I find. So the general syntax is you say Cdo, you say whatever operator you want to have, you say the file that you want to operate on, and you say the name that you want the resulting file to have. And sometimes you can have many files of infinite files. So for instance, if you want to do ensemble statistics, there can be a long list of files that you want to do, take the ensemble mean for maybe, and then you have finally a file where you write the ensemble mean to. So Cdo operators can be really simple, like this one, which just say you want to just add a constant. So here it's adding 1. It might not be so relevant, but let's say you want to move from Celsius to Kelvin or the other way around. Adding a constant to all the temperature variables can be a useful thing to do. So you add a constant from the int file and you get an int file plus 1 file. But Cdo operators can also be very complex. So they can, for instance, do regridding of files. So in this step, we make a grid description file from the whatever file we have with the grid that we want. And we write that to a file called bestgrid.txt, which is a grid description file. Then we use that file using a remapping tool. So in this case, it's bilinear mapping, but there are various different other remapping functions that you can use. And we use this grid. We take the data that are on the wrong grid and we move it to the right grid. Overall, there's statistics and arithmetics on single files or ensembles. There's time concatenations, there's regridding, there's subsetting, there's lots and lots of things that you can do. And here's the URL for the documentation for Cdo. And in practice, you don't go about and just read the whole thing and understand what's there. Sometimes it can be useful to go in the index and try and find which category the type of function that you're looking for is in. But oftentimes, what I end up doing is thinking, I have this problem that I need to solve. And I think it's something that's not, that probably other people also would have wanted to do. And if other people have also wanted to do it, then I will Google that problem alongside NetCDF and Cdo. And likely I will get a couple of hits of people who asked for a solution to the same problem using Cdo. And there will be an operator there that they used. I will then search in the documentation for that operator to find out exactly how to use it. And sometimes it's not exactly the problem that I thought of, but you have to think in terms of what's the more sort of general variety of the problem that I'm trying to solve that might solve it for me, that other people might have done. So let's try. Let's just first have a look at the documentation. So there we go. So this is what the documentation looks like. Let's just put this thing down. So in the index, we can see some different types of categories. There's selections, conditional selections, comparisons, arithmetic, and so on. So if we know what we're doing, we can sort of guess which of these categories to look in. But it's also really nice to search through. So let's say we wanted, so remember we wanted this, we had hourly data from error 5, but we wanted it to be hourly. And it turns out there's an operator for that called day sum. So I'm just going to search for that one. And it gives the daily sum. And in this section, there are a lot of variables of the same kind. And there's not even a, when you look at that, you can often see an example of how to use it, but there's not an example. And when there's no example, normally the easiest thing would work. So what we do is Cdo, and then day sum, and we can take this new file that we just downloaded, and we call it daily instead of hourly, like so. And we run this command, and we see that we get an error message. What it says is that the position in the numbers is too high for this to work. So in practice, what it means is the numbers that we are getting are too large and they don't fit in the 32-bit floats. So, but it also tells us how to fix the problem. So what we have to do is add a little bit more precision to the output file that we get. So we do this by saying -b, that's what size of number of bits for the numbers, and we say float 64, and we do it again, and then we have a working command, and we have a daily precipitation file. Okay, and then we wanted to compare the CAN ESM5 and the error 5, but of course our CAN ESM file data are global, whereas the error 5 data that we have were just for Southeast Europe. So what we might want to do is try and cut from the CAN ESM data just to have Southeast Europe. What we do, let's open up the documentation again. And I've used this a couple of times, so I know that selecting things starts with cell. So I can go through this through a bit of this here, or I could just divulge that it's and I want to select latitude and longitude. So cell long lat box is the correct operator. And here it's an example of that in practice, but here's the part where it's actually documented. And we can see an example of or a documentation of how that's being used, because it's a bit more involved than just the operator and the file names. So we see that we give the longitudes and then the latitudes separated by commas. So that's what we're going to do. And I'm going to cheat a bit, seeing as I've done the this demo previously today. So the command comes out like this. It says set cell lat box, and then the longitudes. Actually, the wrong one. So it's supposed to be 30, not 35 for the second longitude. And then we run that command and we get a new file for the can use M5 data. Okay, so we've looked a bit at CDO, and so in addition to CDO, there's also NCO, which has a lot of overlapping functionality, but also additional functionality that CDO doesn't have. And it's organized a bit differently than CDO. So for CDO, we always had CDO and then some operator and then possibly some other arguments. Whereas NCO, it has we never say NCO something. We have different packages within NCO do different things. So there's NCAP2, which is an arithmetic processor. So that's where we add a 1 or multiply by 2 or do similar things. And we can do sort of more advanced expressions as well in there using NCAP2. Encapted is an attribute editor. So we saw that there's this metadata. Those are called attributes. So if we want to change the units, say, if we want to change the calendar, if we want to change stuff like that, then we can change those strings, those metadata strings using encapted. NCS is for ensemble statistics. NCCat and NCRCat are concatenators of various kinds. So you can concatenate with time, you can concatenate more variables into the same file, and so on. NCFlint is an interpolation tool. So say you have data which is for you have some modeled data which is for every 3 hours, and you want hourly data, but you think that the variable might be okay approximated by a linear interpolation in between them or some other known interpolation scheme. You can use this NCFlint to make up the data in between. NCKS is a kitchen sink, the NetCdf kitchen sink, and it's an operator which does a whole lot of different things. So in a sense, you can say that's just the CDO of the NCO toolbox. So it has a lot more. I'm not going to go into details on that now, but if you search for in this way for a solution to a problem, the same way I talked to you that you could do with CDO, with NCO and Net Cdf, and your problem, you will often encounter solutions using NCKS. NCPDQ is a packaging tool. So these binary files are a way of packaging, but this can be done in more or less efficient ways, and NCPDQ can help you to make the packaging more efficient, or it can also unpack files that have been really efficiently packed. So one way of packing could be to use a mean and a sort of amplitude and divide by that. So all the numbers become rather small numbers between 0 and 1, say, or something like that. And then you have, so your numbers might be, say you have temperatures, for instance. Temperatures don't come in sort of 0 to infinity values. They come in a relatively narrow range. So you can pack the data much more narrowly by sort of doing some manipulations with means and offsets for them. But then when you look at the data and afterwards, they might not be so meaningful in terms of the numerical values of the data. So you can use this tool to unpack again and get more sort of sensible data without means and offset. So NCRA is a statistical tool. NC-remap is for remapping. So NCO also has remapping, and they work slightly differently from CDO. So sometimes the metadata can come out better if you use NC-remap than CDO, for instance. NC-rename can rename variables and attributes. And NCWA is for weighted averages. And there's also NCClimo, which has some climatology tools. Yes, so let's see some of that in practice. So let's start by pulling up the documentation for NCO, and that one fell out of my presentation somehow, so I'll put that link in the chat as well. So let's go back. So this is the general one, and you can click your way to the various sub tools here, and you can also click your way into examples, which might be just as useful for some of them. So if we look at our two files now, just quickly, let's see where's so if we just look quickly at the header of the mechanism, file that we have, we see that the variable is called PR, precipitation flux. And then if we look at our error 5 file for the total precipitation, that file has TP, total precipitation. So it's not exactly the same thing. So we have to multiply by a factor to get the same. But it's also, and the units are different. But we also, if we want to compare them and put them in the same file and do stuff like that, it might be useful to just change the names so that they actually have the same names for the variables as well. So to do that, we use NC rename. So let's look at the documentation for how we use that one. So here's NC rename, and there's attribute renaming, dimension renaming, group renaming, and variable renaming. So in this case, it's variable renaming, and it says we have to have the old name and the new name separated by a comma. So let's go ahead and do that. And then we go from TP to PR in the total daily file. And here we can actually do it without having an output file, so we can do it directly in the same file if we don't send more than one file. Or maybe we can't. Yeah, we forgot the -b. So there we go. And now we can look at the file again. And see, now it's called PR and not TP. Yes. There are lots of different things to do with that. So let's move on. So in addition to working with the specialized tools, NCO and Cdo, we can also work with NetCdf data in Python. And for that, it's really useful to have a library that can handle NetCdf files. So read them into Python or write them out from Python and so on. And I think Tom might have shown you a library already called NetCdf4, which is absolutely nice and useful. But X-ray, which I show you here, is a little bit newer and more up to date, and it's a bit easier to do plotting with. So I think that one's really useful too. And we can use Matplotlib Pipeline, which I believe Tom also showed you, to plot, and Cartopy to plot on mapping projections. And there are a lot more, many more things to do. So for our data, I did some further manipulations of the data, which I can either show you some of, or I can just send you a link of the file, with a file of the commands that I used, and you can try and work that for yourself. And I got the two data sets to conform to more or less the same standards. So what I'm doing here is I'm showing you the part I used to plot the CANESEM data. So I took the CANESEM data and I summed up over the whole year. So it's the total precipitation in the year. Because it's precipitation flux, I also had to multiply by a factor from flux to actual meters of precipitation, and I got this final file. So I put this variable to the file name. I then open a data set using X-ray from this file, and I take out the precipitation variable, and I call it PRC, and that's a PR from this data set. Then I start a plot axis using the plate career projection from Cartopy and show the plot line coastlines. Then I plot that. I use tight layout because then the plot looks better as a file. I put in the title and I save the figure, and then I clear it so I can do the same thing for the error 5 file that I had. And this is all in this whole script, with also the plotting for the error 5 is in the shared data folder. And what I got out is this plot. These plots, so this one for error 5 and this one for CANESEM 5. And as you can see, this one went a little bit further because I used the wrong, so I went too far east with the variable, so that you can see how what you do actually has a direct effect. You can also see that I've regridded the error 5 data to the same CANESEM resolution, because it's a good thing when you compare different data on different resolutions to consider going to the coarsest grid, at least as a first step, because then you're sort of not fooling yourself into thinking that you have better data than you do have. And we can also see that the total precipitation is a bit in the actual. So 2020 from error 5 is a sort of model of what actually happened in 2020. Of course, we've learned from Carly that it's not completely the truth, but it gets a bit higher values than CANESEM, the projection for SSP 585, and there can be many reasons for that. But one of the reasons can also be what Jana talked about previously today about what can happen with precipitation with coarse and highly resolved models as well. So it's not so easy to see if it's an error in the future projection or what is going on, but at least we could plot things and see some differences. So, and now it's your turn. You can download data and produce similar plots for temperature data. You can think about what variables you would want to download for something else you would like to do. To have it not take for ages, I recommend using monthly resolution. It's also in the shared folder that you have, there's temperature data on monthly resolution for both ERA 5 and CANISM 5 that you can use if you don't want to do the download step. But it's nice to think about, and also in terms of the research questions that you're thinking about, how to maybe obtain the data using these various methods. Then how do you need to transform the data? Can you make the plot look more attractive? I'm sure you can make it look more attractive than my plot. Do you want to do a different region, different models? Feel free to look at something completely different. Add observations to plots is something one can do. Yeah, there are endless opportunities, but I suggest maybe we use some of the remaining time to try out a bit.
Yes, we can.